Let's do the share screen. Voila, I think we're good to go. All right, so last time we pretty much finished discussing the basics of the standard model. And then some about it. Slightly better. Okay, so we spoke about quarks, spoke about jets, spoke about running coupling constants. We spoke about decays. And I told you that every time that the particle can decay via the strong interaction, it's likely going to win. And we spoke about conservation laws. I decided to become So I said that there are plenty of conservation laws that occur in each interaction. Let me go briefly. On the conservation laws, we said there is a form momentum, angular momentum, electromagnetic charge. All of this happens at every vertex, right? Vertex flavor, leptonic number. We had lepton family number. Baryonic number. And quark family number. And then we said that all the form momentum, angular momentum, and the charge, they are conserved in all interactions. The flavor is conserved in the strong, electromagnetic, and the neutral weak. Everything involved with the Z0 boson. And the charge weak, flavor has to change, right? So charge weak. So everything involved with the W plus minus. Clearly the flavor changes.
Asaf?
Yes.
Does it have to change?
Yeah, of course. Because you're changing some of the particles have charge, and when there is a W that is involved, then it has to change to a different particle. For example, right?
The W might do the opposite transition on the other side.
Yeah, but it doesn't have to.
Okay, so there are processes where W is involved and flavor is conserved.
No, because in each vertex, the flavor would not be conserved. Right?
Okay, yes.
You can think of, I guess what you're up to is something like, if you have a scattering that is mediated by a W, for example, if you have an electron and a muon scattering, and then you can think of a situation where you have an electron, it interacts via a W, produces a neutron, a neutrino, and then you have a neutrino that comes in and then interacts with a W and ends up with an electron.
Yeah, something like that.
Is it violating anything? At the moment, I can't think of anything that it violates. I'm not 100% sure though if you have anything like that in nature. So this is a question I have to.
And on the other side, you insist on talking about the W, not the Z, because so the Z might, there are also charge conserving processes that change flavor. Say
No, I don't.
strange quark with up or down, I can't remember right now, the one that makes sense. Strange, like strange and down.
This
So
will involve the W. The quark family number is not conserved within the charge charge weak. As far as I know, it is conserved in the neutral weak.
So it's not just because the charge change. It comes with the charge change, but it's some property of the W compared to Z other than the charge.
Yes, yes. You can think of it like that. Correct. Okay, so the charge weak, the flavor changes necessarily. And the things that are conserved in the charge weak are the lepton number, lepton family number, and the baryon number. These are all conserved. However, the quark family number is not conserved. I guess that's what you just meant. Right, so from, let's say the decay of a neutron into a proton, right? Then there is W involved, right? Because one of the down quarks became turned into an up quark. Oh, sorry, that's not a quark family number. That's a quark number. The quark family can change. You can have up to strange. This can happen. So the W plus minus can connect quarks from different generations. Okay, this is a quick recap on what we discussed last time. Any more questions? How do I get rid of that? Okay, if there are no questions, then today we're going to begin the next subject, which is decays and scatterings. So as we already discussed, the most experimental data that we have about particles originate from three types of measurements that can be done, right? So the first is the looking at the bound states. You know, the proton is a bound state, the neutron is a bound state, right? So what we can measure is the spectrum and the quantum numbers of the bound states. Excuse me, just a little bit. Right, so experimental information comes from three types of measurements. So spectrum and quantum numbers of the bound states. Then the second two are the decays. Right, so when we speak of decay, we can measure the rate of a decay, the angular distribution, etc. And the third type is the scattering experiments. So right now, we're going to discuss the last two, the decays and the scatterings, which are very closely connected to each other. Now, I want to ask you, how many of you are second-year students that never studied quantum mechanics or just started to study quantum mechanics right now? Nobody's raising hands. Okay, because I assume when I wrote this course, I assumed that you don't know too much of quantum mechanics, but here I have to use a few things about quantum mechanics, what everybody seems to be at more advanced stage in your career than that. So that's fine. So let's talk about decays. So I'm going to start by saying a few general words which are not, that nothing to do really with the standard model or not even with quantum mechanics, right? So the first thing I want to say is to mention that there is this thing which is called decay chain, right? What is a decay chain? It means they have a particle and then the particle decays into some other particles, but these other particles in turn can also decay into another particle, right? So for example, right, we can think of a tau particle that decays into a muon plus, it will be neutrino tau, of course, to conserve, plus anti-neutrino muon to conserve the muon family number, right? But then the muon itself is not a stable particle, so it by itself will decay into an electron plus neutrino muon plus neutrino electron anti. So this is called a decay chain. That's actually quite common, right? So the outcome of a decay is not necessarily stable itself. So this is something which is being seen all over. Now the next thing I want to mention, or it's a small derivation, is the lifetime of a decaying particle. In fact, this is something that we want to calculate, or something which we measure. But what does it mean, right? So because when you think of it, every particle decays once, and then it disappears. There's something else, right? So what happens in practice is that we have some sample of particles, right, of the same type, same flavor. And as time goes by, our sample gets smaller and smaller because particles in the sample decay, right? So let's assume that we have a sample of N0 particles. Assume we have N0 particles that can decay. Right. So we call, we introduce a quantity which is called again gamma as the probability of decay. Right? This is the probability of decay of a particle per unit time. And this is called the decay rate. It has several other names, but it's called the decay rate. Let's call it. It has other names, but right now let's stick with the decay rate. Now, what it means that now again, as I said, this is a quantity which we will calculate. This is something which we can take the Feynman diagrams and calculate this gamma from the Feynman diagrams. Okay, but let's first say what it means. So it means that if we have, let's say that we have a time, we have n0 particle at time t. So the change in the number of particles within time delta t, right, is equal to the probability of decay of a single particle times the number of particles that we already had at that time. Okay, so the change of number of particles in our sample within time dt is equal to the probability of decay of a single particle within this time, right, times or multiplied by the number of particles that exist at that time. All right, so in equation, it simply states that dn is just minus gamma delta t, or dt, times n. Right? Simply states that the change in the number of particles in our sample within time delta t is just the total number of particles we had times the probability that of each particle will decay. Now the solution to this equation, of course, is straightforward. That gives us n solution, right? N is just n0 times e minus gamma t. Now this is called the universal decay law, from obvious reasons. Now the quantity 1 over gamma, somebody want to guess how it's called? Has a name?
Lifetime.
Lifetime, exactly. Very good. So this is denoted by tau, and this is called the particle's lifetime. Now, just as a comment, often when you read in books, sometimes semi-popular textbooks, right? People speak of half-lifetime, right? So just as a comment, half-lifetime, right? Half-lifetime of a particle, right? That simply means that the number of particles at some time, which is equal to tau 1/2, is equal to the half of the original number of particles in the sample. And so obviously, tau 1/2 is just tau times ln of 2. So they are closely related. It's just a matter of definition. Right, so this is called the particle's lifetime. Is the one we're going to use. Okay, questions? No? What about, let us speak about the mass of a decaying particle. Now that requires a little bit of quantum mechanics. So the mass of a decaying particle. Okay, now think of it for a second from an experimental point of view, right? Particles that decay quickly, and many of these particles that we're interested in, right, are decaying quickly. So they may not live long enough to be detected directly, right? Rather, these particles are identified by tracking the decay products of these particles, right? So, you know, the mass of the particle that decay, right, is just the total energy of products. Of course, it's measured in the particle's rest frame. Now, the equation we had is a probabilistic expression, right? So, which describes the number of particles as a function of time. Now we can think of this equation of universal decay law as representing the quantum mechanical behavior of a particle. So that means that if we know that the particle existed at some time t equal to 0, then we know that the probability this same particle still exists at some time t, right? Or t to t plus delta t is just e to the minus gamma t times dt. Okay, let me write it down. So we can think of the probabilistic expression right, n equal n0 e minus gamma t as representing the quantum mechanical behavior of the particle. Right? So if we know that the particle existed at t equal to 0, the probability of the particle to still exist, probability of the particle still exist at time t to t plus dt is just e minus gamma t dt. So how does that reflect in the wave function description of the particle, right? So how does that reflect in the wave function? So let's start with a stable particle. Right? So if we have a stable particle, let's say it has a mass m0. Right? Well, in its rest frame, this is the energy. So it obeys the Schrodinger's equation. Now, you may argue that the Schrodinger's equation is derived for non-relativistic particles, which is true, of course. But if we go to the rest frame of the particle, then obviously is at rest, so it's okay to use it. And obviously the relativistic equations would reduce back to Schrodinger's equation in the non-relativistic limit. So in its rest frame, its energy is also m0. So we have that I dt psi 0 is just h psi 0, so just m0 psi 0. And so the solution is, of course, psi 0 is just E minus I m0t. We have a free particle in its rest frame, stable, doing nothing, nothing interesting happened to this particle. Right? Now I'm going to turn on some interaction that is going to cause this particle to decay. Okay, so turn on an interaction that causes the particle to decay. Which means that there is some probability that after some time t, the particle will no longer exist, right? Now, since the square of the wave function, right, is proportional to the probability of finding the particle at time t, right? That means that we somehow need to modify the wave function, right, in such a way as that it will, reflect the fact that after some time t, the particle may no longer be there, right? So what we have to do is to multiply the wave function by some term of the form e to the minus gamma over 2t, right? So we have psi 0t, we now have to modify it into psi of t. If it's not relevant to the course, then please don't. If you have questions to ask, then please ask. So psi of t is just e to the minus gamma over 2t, e minus I m0t. Right? When we do that, then we ensure that when we look at the square of the wave function, right? So that means that psi t squared is going to be equal to e minus gamma t. And that reflects the fact that the particle may no longer be there. Right? Now, it's not exactly a description of a decaying particle. It's somewhat an effective description of a decaying particle, right? Because the only thing we really made use of is the interpretation of the wave function as the amplitude of the probability density of finding the particle. Okay, you're all with me? Yeah, this is effective an effective description of a decaying particle. Making use of the interpretation of the wave function as the amplitude of the probability and probability density of finding the particle. Is that clear to everybody? If you've studied quantum mechanics, then there should not be anything new to you. If you have not studied quantum mechanics, then you might find these things a bit. I take it you've all seen them, right? Yes, no, maybe. Yes. Okay. Right. Now we did not make any use of the probability of finding the decay products, right? Of course, the probability of finding either the original particle or the decay product is unity, right? But we did not ask this question, right? We only asked the question of what is the probability of finding the original particle itself after some time t. Now, okay, now since the particle existed over only a finite lifetime, there must be some uncertainty over its energy, right? Because of the uncertainty principle. And this is an uncertainty over its mass, which means that if we measure its mass, right, we will get some value m, which is different in general than m0. Okay, take a second to digest that. Of course, what we're really going to do is we're going to repeat this measurement many, many times, and we will find some distribution which will represent the probability of finding a value of m. And I'm going to calculate this probability right now. All right. Let me just write it down. All right. Since the particle exists over a finite lifetime, there is an uncertainty about its energy, which is really its mass. Right. So if we measure the mass gravitationally, or the invariant mass of the decay product, which is normally what is being done, right, we get a value which is generally different than m0. If we measure the mass, we get a value m, which in general is different than m0. The mass it would have if it was not decaying. Okay, since time, okay, questions? Now, since the time and energy are coupled, right? These are coupled variables, then the way to obtain the energy is by Fourier transform the time dependence wave function. Now I take it that you've all seen Fourier transforms. Yes? Is there anybody who did not see a Fourier transform in a lifetime? No. Is that a no? No, you've never seen it, or no, you've all seen it? One, don't be pointing shy. Okay, so so we make a Fourier transform in order to obtain the energy or the mass, right? In order to obtain the energy, we make a Fourier transform of the time-dependent wave function. Right, so up to normalization, why does textbooks skip it? Because in a quantum field theory textbook, the main textbook, they don't skip it, but here they do skip it. So psi of m, right, is just integral from 0 to infinity of e minus gamma over 2t e minus I m 0t, and then e I m t dt. Proportional to minus I divided by m minus m0 plus I gamma over 2. Again, there are factors of 2 pi, 1 over 2 pi, etc. The square root of 2 pi, depending on how do you choose the normalization. Now, I took the lower boundary of integration to be at t equal to 0 because the particle simply did not exist at t smaller than 0, but choose any other finite value of t0, not necessarily 0. Right? This is because I assume particle did not exist at t smaller than 0. So in order to get the probability distribution to measure a mass m, right? So we simply need to take this wave function and multiply by the complex conjugate. And again, what we get up until some multiplication constant, normalization constant, right? And then we had that the probability probability distribution of measuring mass m is given by psi of m squared is up to normalization is 1 over m minus m0 squared plus gamma over 2 squared. Now, I'm actually quite sure that you've seen this function before. It's so important that it has a name. In fact, it has 2 names. So you may be familiar with one of the names, that I'm possibly less familiar with the second name. What is the name of this function?
Lorentzian.
This is Lorentzian. That's one name I thought you'd be familiar with. It also has a second name. Does somebody happen to know? All right, that's more for the particle physics. That's called the Brightwinger function. So this is known as the Lorentzian. Lorentzian or Brightwinger function. This function is called Lorentzian or Brightwinger. And the particle that it represents is called the Brightwinger resonance. And it represents is called Brightwinger resonance. Brightwinger. So, you know, as you can clearly see, I mean, this is an analog to what you learn in a classical harmonic oscillator, which has some self-frequency M0 and friction coefficient of gamma. Right, so it's the same. This is the first place I think that you encounter that. That's in first year's mechanics course. Right? Questions? The important thing here is that the mass of a decaying particle is not fixed. So when we conduct experiment with decaying particles, then we have different masses that are measured. And this is according to the distribution of psi squared, which is just described here. Let me see if I have. I have a typo in my notes. That's what happens when you try to work on your notes while you're doing other things at the same time. Now, if the particle's lifetime is long, right, that means that gamma is small, then the width of the distribution is narrow. Oh, by the way, I should say, the gamma, I told you it has several names. So one of the names of gamma is the width of the particle. So gamma is also called the width of the particle. So if the lifetime of the particle is very long, right, then the width of the distribution is very narrow, right, and vice versa. Right, so if the particle's lifetime is long, then the width of the distribution is narrow, and vice versa. So I put a very interesting plot. I'm going to show you where this is very useful for. Right, this is how you measure really masses of particles. So if we look of a decay, so example, look at the electron-positron decay into a pair of quark-antiquark. Right, so we have an E plus plus E minus goes into a pair of quark and anti-quark. Right now, this can be mediated by two channels. Right? It can be, the mediator can be a photon. That's a QED, quantum electrodynamics. But it can also be a Z boson, a weak interaction. Both are allowed. Okay. So what happens at low energies? The QED channel dominates, right? This is a QED channel. This is the weak interaction. So at low energies, the QED channel dominates. So if I'm plotting, I haven't really defined to you what is the cross section, but I'll define it in a few minutes. So I just assume that you wait a few minutes. If I'm looking at this cross section in units of picobarn, I haven't defined what is a picobarn, but I'll define it shortly. And that's a function of energy in the center of mass frame. So that's a square root of S, the modulus time variable that we've seen. All right, start from a 0, and let's say this is 100, and this is 200. And sigma in units of picobarn will be something like 10 to the 4, 10 to the 5, 10 to the 3, 10 to the 2, and 10. Right, so we have E plus minus going to Q quark antiquark. Right, and the experimental data would look something like that. Right, because here it would be at low energies, it will be the QED channel that dominates. Right? So if you just do the QED calculation, then you end up that the QED line should go something like that. But then when we take the experimental data, and when we go to higher and higher energies, we're starting to see a deviation. And then when we get to about 90 GeV, then the experimental data would lie somewhere around here. And the plot would look something like that, the full plot. There's some more data here. This figure can be found if you want to look at it directly. Which textbook did I take it from? This is, I think, from Thompson, yeah, chapter 10. Right, it looks something like that. Now, what happens here? Right, when we get to energies which become comparable to the mass of the Z boson, right, then the weak interaction becomes dominant, right? And what we see here exactly, this is the Brightwinger Peak. And this is really the way, this is really how we measure the mass of the Z boson and the lifetime of the Z boson, right? By the width of the distribution. And taking it one step further, this is, by the way, how you could measure how new particles are being discovered, right? Particles that their lifetime is too short. What you really see is just the cross section for scattering or decaying process to occur. And if there is one that can be mediated by a new particle, then you will see this Brightwinger peak. Okay. Questions? Am I going too slow, by the way? Yeah?
It's okay.
It's okay? I can speed up because these things are, I just don't know. What?
It's okay.
I always have a feeling that, this is it's not supposed to be particular. It's supposed to be, there's several courses in particle physics. This is supposed to be the introductory level. So the simplest there is. I can go faster if you want, but I'm not sure this everybody's happy with it. Okay, you know, a comment is that the Lorentzian is really a first approximation because in reality there are corrections, and that depends on the masses of the decaying particle themselves. Of course, for example, conservation of energy necessitates that the mass would be greater than the masses of the decaying products, but you know, these are details that we won't get into. Okay, another example right now. Let's talk about calculation. Right, example. Right, what is the lifetime of a particle that has a width of 1 GeV? What is the lifetime? Oops. Okay, my iPad seems to be. My lifetime. What is the lifetime of a particle having width of 1 GeV? Right. So the answer anybody want to try? If we express it in units of lengths, right, it would be C tau, right? If you put the correct, it should be H bar C over gamma. Now H bar C, we said this is 0.2 GeV times Fermi. It's a useful quantity to remember, and then divided by 1 GeV, that is 0.2 Fermi. That's in units of length. If you want the units of time, tau, right, it's just H bar over gamma. So I can simply divide that by C, right? So it's 0.2 Fermi divided by 3 times 10 to the 8 meters per second. And then we had 10 to the 15 Fermi per meter. So we end up with 2/3 times 10 to the minus 24 seconds. It's very short. That's why we can't see it directly. Right. Questions? Okay, now let's speak about scatterings. Let's go back in time. What was the most important scattering experiment in the history of physics?
Rutherford?
Rutherford, of course. Now, you know what is the amazing story? I just, you know, I read it when I prepared this lecture. I missed that part. Apparently, you know, you learn about Rutherford from elementary school, basically, right? You know that Rutherford carried this scattering experiment back in 1909, right? But you know that he got his Nobel Prize in 1908. So it's actually one of those cases where he first got the Nobel Prize, and then he did an experiment which was even much more important than what he did to get the Nobel Prize for. So the experiment, of course, is Rutherford's name, and it was done with Hans Geiger and Marsden. And what was he doing, right? So the question is, back about 10 years earlier, 1897, right, was J.J. Thomson that discovered the electron. And then there was this Plum pooling model for the atoms, right? And the idea was that, you know, inside the atom, there is a positive charge which is randomly distributed in the atom. such as that it cancels the negative charge of the electrons. Right? Rutherford showed this is not true. He showed that, of course, all of the positive charge and nearly all of the mass is concentrated in a very small region in space, of course, in the kernel of the atom. This is the foundation of modern nuclear physics. So today we treat Rutherford's experiment as a classical scattering experiment. Right? So Rutherford's Rutherford's 1909 is classical scattering experiment. So as I stated already several times, this is one of the main ways in which particle physics are being studied. Right? So what now in modern days we treat Rutherford's experiment as following, right? So he had an elastic scattering. That is elastic, right? Of what? Of light, charged, and point-like particles. Do you know what particles did he use?
Alpha.
Alpha particles, right? Alpha particles are kernels of helium atoms. So it's 2 protons and 2 neutrons. Light, charged, point-like particles. Which are being scattered. So in Rutherford scattering, these are the alpha particles. Alpha particles. That means that 2 protons plus 2 neutrons. The kernel of helium, helium-2, helium plus. We know electrons. Right, this was the source, right? And the target was heavy, right? Again, charged point-like particle from heavy. It really does infinite mass. Right. Charged point-like particles. What was the target?
Gold.
Gold, right? It was a golden foil. So the alpha particles, they came from a radioactive source that he had there, and the target was a golden foil. And of course, the scattering took place by the influence of Coulomb's force. Right? So under the influence of a Coulomb's force. Right, now how did he conduct the experiment? Right, so he had this gold, he had this radioactive source of alpha particles. And behind the golden plate, he had a fluorescence screen, which emitted a short pulse of light every time it was hit by a particle, right, by an alpha particle. Of course, the flash of light was because the kinetic energy of the alpha particle was lost to the matter in the fluorescence screen, right? And it just put the room to be very dark. And you watch this light, pulses of light by the eye, which was aimed with a microscope. So it just let the eye get used to the darkness, and apparently the eye can be sensitive enough to watch that. Now, according to the Plum pudding model, right, what was the expectation? So theoretical. Not, no parentheses. This was a theoretical expectation at the time. Theoretical expectation. The Plum pudding model. So what was the theoretical expectation?
That it will go through.
No, it's a scattering process. You cannot measure. You didn't have any way of measuring the time. Remember, it's 1909. It's been more than 100 years.
Maybe something like Snell's law?
Yeah, close to. They wouldn't even not Snell's. No. What law did you say?
Snell.
No. No. Simpler. Right. It's a scattering experiment.
They bounce off the foil.
That what?
They bounce off the foil. They scatter off the foil and not reach the other side.
Not reach the other side, of course. But what were the expectations? Small angles.
From the original angle.
What?
Small deviations from the original angle.
Small deviations. Exactly, small deviations. If you had an atom that was made of a lot of evenly distributed positive charge, right? Then you have a small deviation. You could have multiple scattering in there, very much like a bullet that gets into a pudding, right? So you might have several scattering, which would all be small angles, right? So the expectations was to have many scatterings at very small angles. Many scatterings at small angles. Right? Pretty similar to a bullet that is shot into a pudding. Right? He knew what was the momentum of the alpha particles that he could measure, I assume. I guess there was some temperature he could measure that. What did he see?
Use scatterings with high angles.
Sorry?
Use scatterings with big angles.
Right. So the first thing he saw is that most alpha particles don't scatter at all. When the vast majority just go through, not scattering at any angle. Right? Now I don't remember the story. How did he realize that there were a few that were scattered to very large angles? Because he needed to put a foil on the other side, and I think that initially he didn't put any because he had no reason to expect that he would see anything in there. But that you have to read somewhere. The experimental results, remember in physics, physics is an experimental based science. So, whenever there is a clash between the theory and the experiment, the problem is always in the theory. So experimental results were a contradiction that most alpha particles were not scattered at all. And a small fraction were scattered at very large angles. By the way, just out of curiosity for me, do you learn about Rutherford scattering in any of the courses? In modern physics or anything like that?
The classical scattering is taught in analytical mechanics.
Where? Which course?
Analytical mechanics, or at least when I studied the course, and when I was teaching the course, it was an example for classical scattering.
Okay.
We used to calculate differential scattering cross section Rutherford scattering with 1/r potential. The quantum, I've never seen that in the course of quantum version.
Okay, no, I think I think this needs to be learned at modern physics or something like that. If not, then this is the place to learn it. It's
Or
very
isn't
fun.
that Kepler problem?
Sorry?
Isn't this Kepler problem?
No. Well, it's you know, first, no, this is not a Kepler problem, right? The classical gravitational potential and the classical Coulomb potential look the same.
No, sure, not the problem that people saw that Kepler solved. But it's hyperbolas with the same energy and angular momentum connections to the impact parameter.
Yes, it would be if it's in the framework of the classical electromagnetism.
Classical, of course.
Yes. Again, I wrote down this is an elastic scattering. So yeah. So a small fraction was scattered at very large angles. This is exactly what you'd expect as if they were elastically scattered from something small and heavy. This is the kernel. This is the expectation. This is the expectation. From scattering elastic scattering. Elastic scattering from small and heavy, small and heavy scatterer. This is of course the kernel. I actually think that historically, Rutherford, the guys who conducted the experiment were Geiger and Marsden, but I think that Rutherford was the one, they could not understand what they're seeing. And they called Rutherford, who was more senior, and he looked at the result and he was the first to understand what the meaning of this experiment are. That's why it's called Rutherford's experiment. So of course, the outcome of this experiment, one has to deduce that nearly all of the atoms' mass and all of positive charge are concentrated in a very small radius. Right, this is the kernel. The size of the kernel is about one Fermi. So this is the inevitable conclusion. Right, nearly all of the atomic mass and all of its positive charge are concentrated in a very small radius. This is the kernel, radius of one Fermi. Of course, to get to this conclusion, one needs to understand the probability of scattering as a function of angle. This is the important thing on here. Okay. Now that naturally leads us to the concept of a cross-section. So the cross-section is a way of quantifying experimental scattering experiments. And it has several important features. So the first important one is something is measurable. So cross-section is a measurable quantity. By the way, again, I'm quite hesitating. This is I I can't spend more time explaining Rutherford experiment because it is so important, but again, if you know it already, then I should not spend any time on it. So let's say that I'm giving to you as a homework to make sure that you're familiar with Rutherford experiment. Right, you find, of course, plenty of material in any textbook and also in any Wikipedia and any online place that you want, right? It's one of the most important experiments in the history of physics. Okay, so make sure that you fully understand what was this experiment and what does it mean, what people thought before and what people realized after. Okay, right. Any questions about that before I proceed? Questions? None? Okay, so the cross section is a measurable quantity. What's the dimension?
Area.
Area, that's true. So length squared. And again, very importantly, this is a quantity that we can calculate theoretically. Specifically, it is proportional to the probability of the diagram that describes the scattering process. I don't think I'll have time to start it today, but we'll do it next lecture, so next week. Now, just as a reminder, not a reminder, just to get a feeling. Are you familiar with Fermi's golden rule in quantum mechanics? Did you learn Fermi's golden rule?
Could you remind me, please?
Fermi's golden rule? The name rings, does the name ring any bell to you?
Yes, but I don't remember the exact rule.
If you heard it but you don't know what it means, then it doesn't really mean much. Again, I'm hesitating. This is something which you're supposed to learn, I think, second course in quantum mechanics.
Which I'm in the middle of.
Which you're in the middle of, yeah, right. So, but I'm not. When I plan this course, I'm not. This course is designed for people who did not study second course in quantum mechanics, because then it'll have to be a master's level course. Okay, I'm not sure if I have time to fully develop it. I actually think I don't have time to fully develop it. I will introduce it and I will explain it. And I may develop it. It's a bit technical. It's not too difficult to develop actually, but it just requires half an hour. I'm not sure I have half an hour for that. Maybe I will. That tells you, you know, the probability of scattering essentially, in the quantum mechanical way. Okay, so the cross section can be calculated theoretically. That's the important thing for our purpose. And it is proportional to the probability of the diagram that describes the scattering process. Let's focus on understanding what it means. So let's assume that we have a particle A that is moving towards a particle B. Right? So, you know, A can be the alpha particle that is moving toward the gold, right, in Rutherford experiment. Right? So, you know, we are conducting this experiment, and now we can ask questions with, you know, some quantities that we can measure, right? But that depends on the outcome of the scattering process that we're interested in. So, you know, what type of questions that we may ask, right? So we can ask questions such as what fraction of the alpha particles will be scattered at angles which are greater than 27 degrees, right? So when we conduct a scattering experiment, we can ask various questions, right? Such as, what fraction, e.g., what fraction of the alpha particles will be scattered to angles greater than 27 degrees, right? What fraction will be scattered at some range of angles, right? And 27 to 27 plus delta theta, whatever, right? If the scattering is inelastic, then the new particles will be produced, and we can ask in what fraction of the collision certain particles will be produced, right? In what fraction of collisions certain particles will be produced. Right. In what fractions of collisions at least one photon will be emitted, right? What fraction these photons will have an energy of at least greater than something, etc. Now remember that in quantum mechanics, as opposed to classical mechanics, in quantum mechanics, we cannot really make a prediction exactly, right? It's impossible to exactly predict what the outcome of each collision will be, right? The only thing that we can do is to calculate what is the probability that something specific will happen, right? In quantum mechanics, we can only find or determine the probability that something specific will happen. Now for our discussion, let's start from the simplest one. So let's look at elastic scattering and do it classically. Right? Classical elastic scattering. Classical treatment. Right? So in a classical treatment, the outcome is precisely determined by the conditions of the incoming setup. Right? So if we know the initial conditions, we know precisely what is the outcome is. Right? So specifically the outcome of the scattering process is entirely determined by the parameter. This is known as the impact parameter, which is denoted by B. Right? So if we have a particle that is being scattered with another particle, right? So this will be the scattering center. And classically, the impact parameter is the distance in which the incoming particle would have missed if it kept in a straight line, right? So the incoming particle, is being aimed towards the target, the scattering center, and then let's say it's being scattered, so it will move somewhere like that, right? That if it were not influenced by the target, then it would continue, right, in a straight line. Of course, this is the scattering angle theta, and the distance that it misses, it would have missed, this is called B. This is the impact parameter. And of course, ordinary scattering experiments, the smaller the impact parameter is, then the larger the deflection angle is. But of course, the precise dependence of the deflection angle theta on B is it's a function of the potential that is involved, right? Now, although classically, so okay, do I need to define the impact parameter? Let's write it down. Right, impact parameter B is the distance. This is a classical definition, right? The distance in which the incoming particle would have missed the scattering center had it continued along its initial trajectory. Okay, so despite the fact that in the classical scattering the outcome is fully determined, it is still useful to speak about probability, right? And the reason is that although classically everything is determined, practically there is no real way of measuring the impact parameter, right? This is good, if we play billiard, but when we speak of particles, subatomic particles, or even atomic particles, right? There is no real way of measuring what is the impact parameter. So the problem is that B, however, practically B cannot be measured. It's not directly. So what do we do in an experiment? We use a beam of particles, right, that contain many type A particles that interact with the particle, with the target that contain many type B particles, right? So possibly what we really do is we have two beams of particles and we let them interact with each other, right? So experimentally, we use beams of particles. Right, so the next thing to define is a thin target versus a thick target. So what is a thin target? Too slow. What is a thin target for a beam of particles? Very wild guess.
Just one particle?
No, it's a target. It's more than one particle.
Maybe it's well collimated.
No. No, you're not with me. Want to define thin target versus thick target?
One atomic layer.
Nearly, it doesn't be one atomic layer actually. For the target to be thick, but it does have to have one thing, which is what?
One atomic layer.
No, that would not be the definition. What we care about in scattering processes, right, is the number of scatterings that we'll have between the beam and the target, right?
Perhaps less than one collision.
Yes, exactly. That's exactly what I'm looking for, right? So a thin target is a target in which, on the average, there will be every incoming particle will undergo less than one collision. Now, it can be many atoms thick, but the probability of collision is what we care about. Right? So a thin target is a target in which the particle undergo an interaction on the average with a single atom at most. So that mathematically, that means that we can ignore, or we can neglect the probability of a particle to undergo more than a single interaction, right? So particle undergo an interaction with a single target atom at most on the average. Then we can neglect the probability of interacting with more than a single atom. Right? What is a thick target? Very wild guess.
Multiple collisions?
Exactly, multiple collisions. Right? On the average, a particle will undergo many interactions. So if we want to study the basic interactions between the particles and the targets, what are we going to use? Thin or thick?
Thin.
Thin, of course. Well, what are thick targets used for?
When you want to understand the interaction in a system, in a larger system.
When I want what?
To understand what happens in the context of a large system with multiple things, not just a particle and particle.
No, then I will use Fick's law and other things. No, it's really to stop the particles, right? If we have a beam, we need to stop it for safety reasons, or if we want to produce new particles. That can also be quite important. Right? So we mostly use targets. That's okay. So for simplicity, right, we can think of the target. Oh crap! I'm running out of time. Oh, I'm going quite slow, which is kind of surprising me because this is something which I thought would go like that. Can I grab another 5 minutes of your time? I'm not sure we'll finish in 5 minutes. Okay, so if you want to study physics of interactions, we work with thin targets, right? So consider a target that is only a single atom, right? So consider a target that contains a single atom. Right, here we have a single atom, right? So we define the beam flux as the number of particles that we send to the target per unit time, per unit area. So the beam flux, right, denoted by phi. Right, this is the number of particles we send to the target per unit time, per unit area. Right, this is number per centimeter squared per second. Right. Of course, the higher the flux, then the more particles will hit the target per unit time. Right. Or if more particles hit the same number of particles hit the target, then the impact parameter is smaller. Right. So the rate of scattering events that occur for a single target atom is proportional to the flux of the incoming particle. Right, it's obvious. So the rate of scattering events occurring for a single target atom or particle, right, is proportional to the flux of incoming particles. Right, so the number of scattering per unit time is proportional, and the proportionality constant is sigma scattering times the flux. Right? So NS is the number of scattering events, and the quantity sigma S, which has the dimension of area, is called, right, sigma S has the dimension of area, that is called the cross section. Right, so this is a definition of the cross section. Again, we know what is the flux of particles, so we know how many particles we send into the target per unit time, per unit area. This is, we control the experiment, so we know that, right? And dns over dt, this is the number of scattering events which occur per unit time. This is something which we measure. So on the left and the right hand side, these are something which we measure. Then we know what is the cross section. Now, of course, this is somewhat simplistic, right? But because normally we don't have a single atom, but if we have right, NT target atoms, target particles, use particles. Right, then the rate of scattering event is multiplied by NT. Right, then we can define the luminosity as the flux, which is multiplied by the number of target particles. We define the luminosity. Right, L is just the flux times the number of target particles. And of course, what we have is that the number of scattering that occurs per unit time is just sigma S times the luminosity, because now we have many target particles. Right? So the cross section has units of area, and in particle physics, the typical the unit is called barn. So in particle physics, the cross section is measured in units of Born. Symbol is B. So 1 Born is 10 to the minus 24 centimeter squared, or 10 to the minus 28 meters squared. Now, typically, Born is a very large unit. The cross sections that people deal with for most processes of interest are measured in much smaller units: milliborn, microborn, nanoborn, picoborn, femtoborn, even attoborn. And these days, people discuss about detecting dark matter. The unit is smaller than that by several orders of magnitude, because the cross section for dark matter would be something of the order of 10 to the minus 44, 46 centimeters squared. So 10 to the minus 20 something barn. So barn is really something which is quite big for a particle physicist. Right, so we have milliborn, microborn, what else? Nanoborn, picoborn, femtoborn, attoborn. Now again, L, I want to stress again, L here is something which we measure. Right? This is the experimental setup. This is set by the experimental setup. And this is something which we measure. So we can calculate what is the cross section. Okay, there is two more things I want to say, but I think we are running out of time, so I can do that next week. Just, classical example, right? The billiard ball example, right? If we have a beam of point-like particles that hit the target of particles that are heavy and spherical of radius r. Right? So, example. Right, point-like, a beam of point-like particles. It's a billiard ball, right? Point-like and light particles hitting a target of heavy particles. Which are spherical and radius r. Right. So, right, so a scattering process happens if one of the beam particles actually hits the target. So what is the cross section here? Right, so we have a point-like particle. It's a target.
Pi r squared.
Of course. Sigma scattering is simply pi r squared. Of course, this is the simplest possible example here. Okay, what we really care about is the differential cross-section, but since I'm running out of time and it will take me another 5 minutes to define, I'll do it on next week. And then we'll move to the quantum mechanical commitment. Questions?
תודה רבה.
Okay, right, I'm asking again, I have a feeling this is something which I thought would be like peanuts, because there is nothing which is conceptually difficult or technical here in this lecture. So somehow I thought it's going to be faster, but it turned out that I'm doing it slower. So I'm asking you again, if you feel that I'm going too slow, just let me know and I can speed up things. my interest is that you understand everything I say. So, even if we don't go through everything, and we won't go through everything in this course, because I told you in advance that I'm not teaching you quantum field theory, and without quantum field theory, we cannot go into the full technicalities of everything. But the purpose of the course is to give you an overview of what is particle physics and what particle physicists do. And of course, we will get into technicalities, but up to a level. The level is supposedly appropriate for undergraduates, so people that it's not a master's level. But if everybody feels that I should go faster, then I can easily do that. It's a bit up to you. All right. So feel free to let me know. Shukai, send you an email. All right.
Thank you very much.
Thank you. Next weekend. And I'll see you all on Tuesday.
Yeah.
Thank you. See you.
All right. Bye-bye.
אני מזכיר לך, יש לנו היום הרצאה של מועמד.
אנחנו יודעים.
סבבה.
צריך להיות חלק מהרקורדינג.